All right, guys, I think we'll get started. Can everybody see the board? Yeah, is it too bright? Not bright enough? Okay. All right, so I'm sure you're all very excited about your first midterm in machine learning. It's happening on Monday. Get the date right. We had people emailing about forgetting which day the homework was due. So it's on Monday, and it's going to be here in class. You're allowed to bring one page, like a cheat sheet, so front and back. You can write whatever you want, make the font size really small, we don't really care. One thing is that be able to read your cheat sheet and be able to find things quickly, because that will really, really help you on the exam. The time is like the most limiting factor you have on the exam. You are not allowed to bring anything electronic. No cell phones, no computers, no iPads. If we see you using any of them, we will kick you out. And you will not need to bring a calculator. So if there are any calculations that are on there, like probabilities maybe, and you can just write out all the terms, and we will count that. Like, it won't make you compute like the final solution. Okay, I'll wait till everyone sits down. Okay, so for those of you who just came in, I just said the midterm is on Monday. You're allowed to, but you're not allowed to bring electronic. So one of the things that people do when they get to the exam is they open it up and they start to panic because, oh my God, it's so long, hard, whatever. So don't panic. That is the worst thing you can do for yourself on this exam. Just try and stay as calm as you can, and if you don't recognize stuff, then you'll work through it. If you did not go out drinking the night before and you've sincerely studied, then you know more than you think you know, okay? So just give yourself credit and calm down and work through the problems. Start with the easiest ones first and like keep going from there. Lastly, make sure you help us give you points, okay? Think of this as like a technical interview. So if you've ever been in a technical interview, they want you to like think aloud, right? Because they're looking for your process as well as the actual solution. So if you get a question you have no idea what to do, but maybe you know something about it, make sure you write down that something. If you get a problem and you're running out of time, tell us, like maybe you can't do the derivation in time or something. Tell us how you would do the derivation in like point form, and then we can at least give you some credit. If you give us blank, then there's nothing we can do. And lastly, I just wanted to advertise the office hours. So there's office hours every day from now until the midterm. So if you're working on something or you're going through slides and you catch a snag or whatever, come and see us. Like, we pretty much have morning and afternoon covered until the midterm is done. And tomorrow, Jeff is going to do a special recitation, so it'll be less structured than this one. He'll just basically take your questions.
What time is it?
It's at 6 o'clock tomorrow. I believe it's here. So does anyone have any questions about the format of the midterm? Yes?
Was the practice test the actual test last time?
No.
That
So this test actually took me about 5 hours to do myself. The thing that I gave you guys. So yours will not be this long. No. This was meant to give you practice on a variety of topics and also on a variety of different styles of questions that we could ask you. Okay, so I took them from like all over the place, like different midterms, textbooks, whatever. Yes?
Will there be topics covered on the midterm that weren't covered in the practice?
The topics covered in the midterms are exactly the topics that Jeff posted. So it's possible there's not a one-to-one correlation between what's on the midterm and what's on the practice questions. Okay? So your test will have like some true and false, then some short answers. So it could be multiple choice, like give us a short answer, and then there will be a few longer sort of problems. Anything else? Okay, so how many of you have done the first page of this? Raise your hand. Okay, all right. So when it gets to like no one's done the questions, I'll go a little slower, but. All right, you can't see that, okay. All right. Okay, so the first question, I guess I should zoom in a little bit, is no classifier can do better than a naive Bayes classifier if the distribution of data is unknown. So how many people think it's true? How many people think it's false? Okay, good. So on the actual test, we're going to ask you to give true and false, and we're also going to ask you to give an explanation, okay? There's two reasons for that. One, you cannot guess randomly and get a point. And two, if we make a mistake on the question, then in your explanation, you can tell us what your assumptions were, and you might get like 2 points even if your true or false was wrong, okay? So I'm going to write out the explanation for this. So false. This is question A. And basically the explanation is that naive Bayes assumes that all features are conditionally independent given the class. And it's this assumption that limits its performance. And this has nothing to do with knowledge of the distribution. Okay, so B, I actually made this harder than I thought I was making it. So linear regression, maximizing the likelihood of linear regression yields multiple local minimums, true or false? Who thinks it's true? Who thinks it's false? Okay, so the actual answer is it's true. And here's why. Okay, so all right, so linear regression, actually, let's do it this way. Remember what it means to be convex, okay? So convex means that you have multiple local optima, but that all of them are the same value. So strictly convex means that you have one optima, and that optima is global. So what I'm asking here is basically, is linear regression strictly convex? And if you remember, the last time I did recitation, I had you derive the first derivative, and then the Hessian is actually equal to 2x transpose x. And so we need that to be positive definite for it to be strictly convex. But this is only true if X is full rank. So in general, it's not true. In general, it will have multiple local minima. Is everyone good? All right, C. So if the function is not twice differentiable, that is, the Hessian is undefined, then it cannot be convex. True or false? Who thinks it's true? Okay, you're right, it's false. So for this one, the easiest thing I would do for an explanation is to give a counterexample. So yes. So if it is differentiable except for, sorry, I don't understand the question. So a counter would be something that is not differentiable but still convex. So not twice differentiable but still convex. So in that situation, depending on whether like what you're suggesting is convex. So that's what I'm getting to actually. So so the counterexample I would give is L1 regularized regression. And the objective is y minus x beta squared plus beta, like that. And this is convex because this is convex, and this is also convex. So when you have the sum of two convex things, then this is also convex. But you cannot differentiate this. Okay, next. So D. Yes.
I mean, the L1 norm of beta 1 is not twice differentiable, right?
Right, it's not.
But you haven't said why it's still convex.
So do you agree that the individual parts are convex, and there's a property that says if you sum like two functions that are convex, then the sum of that is convex. Why is it not differentiable? So you look at, so L1 looks like this. That's what it looks like. So it's differentiable at this point, which is 0. You could use the second term if you wanted to. I just picked this because it's an objective that everybody knows about. Okay, moving on. So ridge regression. Ridge regression, linear regression with an L2 penalty is a convex function. True or false? Who thinks it's true? You're right. So it's true. And for the same reason that the other thing is false, so this one is written like this. We'll leave that squared. And so both parts are convex. So the whole thing is convex. Okay. Any questions before I go to short answer? Yes?
When you are talking about ridge regression and linear regression are functions, are you saying that it's a matching between the input data to the
Okay, so I would say, so when I'm talking about the linear regression, ridge regression, I'm talking about the objective of those two. Yeah, the objective function. Yes. I am talking about the, no, I'm talking about the objective function. Come and ask me afterwards, okay? This might require a longer explanation. Okay. So we're going to move on to short answer. All right. So how many people did this question? Okay, a few people. All right. So explain how you would do tenfold cross-validation to choose lambda for L1 regularized linear regression. Okay, so what I would do for this is draw a few pictures. So for this question, there's actually multiple answers because not everybody in the machine learning community agrees. But as long as you get one of the right answers, then that's good enough. So what I do is I divide my data into training data and test data. Okay, and then what I do is I consider only the training data when I'm doing tenfold cross-validation. So for the training data, I do it so 10 times, 1. So I get an X, we'll call it train 1, an X train 2, and all the way down to X train 10. And then similarly, I guess this should be a Y1 train, Y2 train, Y10 train. And what I do for that is for each lambda, I randomly sort of like split, and this is, by the way, 90% of the data. So these guys are 90% of the data, and then I'll have an X1 test and Y1 test, and this is going to be 10% of the data. So for each parameter, for every one of these splits, I find the test error. And then I get the test error here. And then at the end, I basically sum it up. So total test error. And then what I'll get is I'll get something that looks like lambda. And then I'll get like different test errors for different lambda. Actually, the curve should not look like this. So it should be as you increase lambda, so it should be like this. You should get something like this, and then you pick the optimal lambda. And then once you have the optimal lambda, say this one, then you plug it back in for your test data, and then you find out like the final fit. And then you get a beta out of there. You use a range of lambdas. So you would use, I don't know, 0.001 to like maybe 10 or something. Depending on your application, it depends on how you pick the range. So when I do stuff, I usually try like a lot of them, and then I narrow down the range, and then I try that range, usually about 20 lambdas. Sure. So you just saw it actually. It's, y minus x beta. That's the objective function. Yes?
So we find n different optimal lambdas.
No, you're only going to find one optimal lambda. So when you're doing the tenfold, you're just same lambda for each one of those folds. And then at the end, you get a total test error. Sorry. There we go.
Sorry,
Yes.
once again, 90% of the data is training data. I split myself into 9-1, and I train on everything, and I test on the test data, and I plot these lambdas.
So yeah, so some people will take, the original split, some people will take 90% of all the data, and that is your training data. And some people will actually take, so a certain percentage of the data is training data. So say I take like an arbitrarily, say I take like 80% of my data to be training data. Then within that 80%, I'm going to do the tenfold. So I'm dividing into 90-10 splits. And then I keep the test data separate, and then I test it again. So this all depends usually on how much data you have, what you can afford to do. Some people will just take the data and divide into 90-10 randomly, and then not keep an extra holdout test set.
But wouldn't you have to do it like 10 times inside the training data?
Yeah, so no. So I'm saying some people don't actually divide the data into a training and a test, and then do a tenfold inside the training. They'll just take their whole thing as training, and then do that. If you don't have a lot of data, that's sometimes what you have to do. Come talk to me after. Yes.
So each time you train a model, are you training it on like 0.1 times 0.9 times 10?
Yes. Yeah.
I think I've seen it in the past where each, like, you divide into 10, but then you take 9 and then you train it on that and you test it on the other one.
So that's leave one out. Leave one out, cross-validation. So that's not necessarily 10 data points. What you can do is you can train on 9 of them, leave one out, test on that one.
But I'm saying you have 1,000 data points.
Okay.
You leave 100 out.
Okay.
9, 100.
Yeah. Okay. So I think I think we're all confused about the same thing. So let me just be clear. All right. So here's your entire data set. Okay? Now, what I was saying before is that you do, and this becomes your test, and this becomes your train. Okay? So now I'm going to take the train out, and I'm not going to touch the test for. So then what I can do is I can divide this up into 90-10. Go back to my original test set, and I'm going to fit beta based on this lambda. If you have a lot of data, this is what I suggest that you do, because you're keeping your test set complete. If you don't have enough data, what you can do is you can use this whole thing. Sorry? So the optimal lambda is going to be the one where you have the lowest total test error. Yes. Okay, so what you would do to get the beta is So your objective is y minus x beta plus lambda beta. Right? So in this situation, there's the first one is, yeah, an L2 norm. You could think of it that way. It's squared error. So once you've gone through cross-validation and you know your lambda, then you can just plug your lambda in. So you can plug in the optimal here. And go about solving this optimization problem. That's how you get beta. Yeah, so what you're saying, yeah, what are you saying you're doing? Can you guys please not talk? If you want to discuss it, go outside and discuss it and come back. Thank you. All right, so what you're saying is, so on 90% of your data, so let's say we have a range of lambdas, 0.01, 0.05, 0.1. So this is the lambda space that we want to see, which is the optimal lambda. So we have our 90% here. And basically what we're going to do with this data is we're going to say lambda equals 0.01. And then we're going to take this objective and we're going to fill in lambda here and we're going to optimize for beta. So once you have your beta, so here we're going to have lambda and beta. Once you have your beta, then what you can do is on your test set, so this is your test set, you can actually compute the value of the objective. Or usually just compute the squared error. So here you can compute the squared error. And split. And for the same lambda, lambda equals 0, you're going to what you're going to get is 1, 2, 3, 4. You're going to get 10 of these. You're going to get 10 of these. Total test error. Okay? Do this for every single lambda. For every single lambda, you're going to get a total test error. And then you look at which one is the smallest, and that's your optimal lambda. And then if you had lots of data and you held out a test set here, so plug in lambda there and determine the beta. And that's going to be the model that you choose.
When you find the beta, you test against all the data, right? Not divide. You don't divide anymore.
Yeah, when you find your optimal beta, then you're gonna do it on your test set.
Only test that you don't. So basically dividing 90%, 10%, and you minimize, find beta minimize from x. So when you find beta, you consider 100% instead of 90%.
No. Okay, so let's come up with different names because this is still confusing. All right, let's call this test and let's call this train, and we're going to call this is the training data, and we're going to call this the validation set. Okay, and we're going to call this the I don't know, double train set. Okay? So this test set, don't worry about it right now. We're going to hold that out. It's going to be we're not going to learn on that set, okay? So from the training set, we're going to have 90% and 10%, right? And we're going to divide it randomly into 90, 10 times, okay? So from here, what we're going to do is we're going to get 10 errors. So do you follow me so far? So we're going to get 10 errors. We're going to pick the best one. We get our optimal lambda, lambda star. Okay? So after we've done that, then we take the lambda star and we put it back into the test data here. And then using that, we're going to find beta. And that is the beta. That's the model that we want. Clear? All right. Yes?
We learning beta during the cross validation, right? For each lambda, we will be learning one beta to actually find.
Yes, but so the beta that you keep at the end is going to be the beta that you learn from the test set. Okay. But yeah, so each time you're actually going to learn a different beta.
And the error that we get with that beta is what we want.
Sorry?
The error that we get with each of those beta is what we want.
Yes, yeah. But you're going to plot the total for every split, right? Yeah, so for each lambda, you should have one error point. All right. I didn't realize that was going to be so confusing. Okay, so let's move on. Okay. So this one's an easy question. Why does the kernel trick allow us to solve SVMs without significant inducing? And the answer is basically, so in the dual, of the SVM. Features appear, dot products, which are represented compactly by kernels. And if I was writing the test, I would just write out yeah, sorry. Thought I was getting better at this. So I would just write out the objective and show that this is your kernel. Okay? So next. How is that looking? B. This is C. All right. So this question is basically testing your ability to take the dual something. Okay. And this is the type of question that people panic over. So I'm going to go through it slowly. The one thing to remember is that on the exam, you might get something that looks kind of strange, okay? You've never seen it before, it looks weird, it has complicated symbols. Just remember that you are taking the dual and know how to take the dual by heart so that on the exam you won't be freaked out if it looks weird. Okay, so the first thing you want to do is you want to write down the Lagrangian. So the Lagrangian can be written as follows. Okay. So after we do that, we're just going to Okay, and then just regrouping. Okay. So that's the Lagrangian. So if you do nothing else on a problem, write down the Lagrangian. You will get points for that. So now, in order to get the dual problem, we have to maximize over lambda the minimum over x of the Lagrangian. Okay? And so in order to get this, what we need to do is take the derivative of the Lagrangian with respect to x. So we're going to do this. X equals. Okay, so this is the point that minimizes the Lagrangian via x. So once we get this, we actually have to plug it back into the Lagrangian. So then we're going to get okay, so this is going to cancel. Oh, yes, it is. Thank you. Okay, and then that's basically it. So that's so the final dual problem is just to maximize this. It's greater than 0. So when I took my midterm in 701, it was, I believe it was like taking the dual of something that I messed up at the end. Like I just ran out of time and I couldn't finish it. So what I did was I just wrote down like how I would have taken the dual, and I think I got maybe half point or a point or something. So definitely do that if you're running out of time at the end and this is the one you've left. The constraints to put down? So the constraints actually come from your actual, like, so basically when you write down the Lagrangian, you say that lambda, blah, 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 you add this, right? So this has to be greater than 0. If it was 0, then you basically didn't add anything. As for why it's not negatives less than 0, I think the easiest way to see that is using the KKT conditions, which I don't want to get into right now.
You also write constraints in terms of two constraints, say x tends to x minus 2 times n for x here, so x between 2 and 4. So x less than 4 and x also bigger than 2. Then two constraints, right?
So what x is? Well, it doesn't really make sense to write the x constraints in the dual because you basically subbed in the optimal part.
In the original constraint, you have so basically x between 2 and 4.
Yeah. So the original problem probably has more constraints.
You have two diagonal multipliers in that case, right? So you have x bigger than 2 and x less than 4. You have two multipliers because you have two constraints.
Are you talking about the primal problem?
Primal.
So the primal, okay.
Right, so I'm saying that we can reduce the quadratic to linear. Or otherwise, we know that's x between 4 and 2. X bigger than 2 and x less than 2.
I can't follow you right now. You can come and talk to me after. Yes.
I think our final constraint is equivalent to linear constraint because x is between 2 and 4. So if it is equivalent to x greater than greater or equal to 2 and less or equal to 4, so we could use these constraints to derive our problem.
You might be able to. I'm not sure if I can answer your question off the top of my head, though. So come and talk to me after. Okay. So, okay, we're going to not go in order and make are really important. So we're going to move on to SVMs. Okay. So I should use something else. Okay. It's hard for me to write without this big cricket. So this problem, if you got it on a midterm, might actually look scary, but it's not actually. So the first thing I would do is, if you see this long paragraph, is figure out what exactly you need to know. So it tells you that you're training with the SVM with a quadratic kernel. So that's really important because you're going to get a quadratic decision boundary as opposed to a linear decision boundary. And it also tells you binomial kernel of degree 2. So you can't have anything like too wiggly because you only have a degree of 2. So you're given this data, and then they tell you that there's a slack penalty. Okay, so the question is, what would the decision boundary be for very large values of C? Draw on the figure below. And the figure is at the back. So the answer basically is that if you have a very large slack penalty, then it's not going to hang on one second. It's not going to penalize, it's going to penalize misclassified points very heavily. So maybe what I should do is write down the objective. Okay. So let's write down the objective. plus C subject to, so this, I've just written down the primal. Okay. So for very large values of C, this is going to be huge. Say like 1,000 or 10,000 or something. And this is a minimization, right? So if we're penalizing this very hard, then we want this to be a small quantity, which means that we're basically penalizing shrinking the margin. And that means that we're penalizing misclassified points. So what it's going to do is it's actually going to have, it's going to separate it out perfectly. So the second question is that C equals 0. So that means this is 0. So that means it doesn't really care about penalizing some misclassified points. So we can misclassify a few and maximize the margin. So for this one, it's probably going to do something like this. Next question says, which of the two cases above would you expect to work better in the classification task, and why? So remember in the classification task, it says somewhere about sensors. So the training data is coming from sensors, and this can be error prone. So you should avoid trusting any specific point very much. That's really important. If you see, like this case here, it's pretty much overfitting a little bit to these 2 points. So given that information, for 3, we would pick this one, where C is equal to 0. So number 4 is draw a data point that will not change the decision boundary learned for very large values of C, and justify your answer. Okay, so we know that for very large values of C, it's going to try and classify every data point correctly. So if we're going to add a point, we have to add it somewhere where it would already be classified correctly with the original classifier. So what you would do is you would probably put a green point here somewhere, or in here. Anywhere in this area is fine. Sorry? Oh yeah, or you can put, okay, yeah, you can put a point here if you want that's red.
Or a white point anywhere.
Or a what?
Or a white point anywhere.
I'm not sure if you would get points for that on the midterm. It depends on what kind of mood I'm in. Yes? No. So you're saying putting a red point here? So that would actually change the decision boundary. Yeah. Well, it would, like, it depends where you put it. If you put it here, it might not do anything. If you put it here, it'll change. It'll try and probably do this. But I wouldn't recommend doing that, because then we have to be like, oh, okay, did the student actually understand? If you understand it that well, you should put what we're thinking. You should put. Yes.
In one of the lectures, I remember he made some kind of argument about if the data was separable, one of these penalties doesn't have an effect. Is that a different case from what we're talking about here?
So I guess if this is, so if these 2 points here were over here, then the data is easily separable. So then the slack penalty Let me think about it.
Do you remember the CSS file I'm talking about?
No, I don't.
Then someone else? Yeah. Okay, so why does this problem fit that?
I think we mentioned that if the decision boundary already classifies the two, and then in increasing C, beyond point will not be an issue.
Right. So in the first question, when we drew the decision boundary, that separates the correction, right?
Yeah, so now you're adding a new boundary to it. By the way,
Oh, so that means part B, why am I here black?
because in part B, the value of C is not high anymore. Yeah. Part B, the value of C is tending to 0. So if you
But by reducing C, you change the boundary. To get the one in the top right.
Okay, so what is the consensus? I don't have the slides memorized. I'm sorry, guys.
It sounds like you can increase C without changing anything, but reducing C changes things. That's what makes sense. Yeah, like if you increase C further than it is in the top left, it will change it.
In the top left,
Yeah.
if you increase C further, yeah, I agree. Yeah, so I think what he's asking is if you set C, and you already like classified all the points correctly, if you increase C, is that going to do anything? So no. Okay. Let's move on to number 5. So draw a data point which will significantly change the decision boundary learned for large values of C and justify your decision. So you have to add a point that is misclassified. So what I would do, the easiest thing is to add a red point here. No, closer to the other way. Classify, yeah, so add a green point here. If you add a green point here, then this decision boundary is going to have to stretch to get it. Yes?
So the decision boundary in this case is limited to quadratic shapes.
Yes.
It doesn't matter the rotation of the quadratic shape.
What do you mean? Like,
So that's like that quadratic shape is like rotated at 45 degree angle.
The top one's technically not.
Well, it's very spread out that way. Of course you'd be able to turn it, otherwise this would be pointless. You would never be able to classify things if they were the other side. So of course you can rotate it.
yeah, I think the quadratic function can be rotated. I'm not actually sure off the top of my head what mathematical thing to tell you about to relate to that, and I think for the purposes of the exam, you should assume that it's going to be able to. Okay. In a large margin, what does that mean?
Like, because the rotation of the parabola would change the margin, right?
So I think the margin is kind of like this abstract concept to describe sort of like how you're, like the distance, the amount that's actually separating your points. So I'm not sure exactly if I understand your question.
So if we can freely rotate the parabola just to get the points separated,
Mm-hmm.
we will get different margins. So wouldn't that matter? If
Wouldn't
we
that matter for what?
for maintaining the largest margin possible?
So,
Maintaining the largest margin possible and being able to rotate the parabola freely seem to be kind of inconsistent.
why?
Because the recitation would limit that margin. May limit that margin.
So I think the answer to your question is that you're thinking about support vector machines the wrong way. So I think you should think about this as a classifier and the fact that you are trying to separate your data. You shouldn't think about it as there's this abstract concept called a margin and we're trying to like push it apart. You can come and talk to me after if you're still confused. Yes.
For part 5, when you place the point among all the like, what would the new margin look like?
Okay, so the new boundary, so it would look like this.
If you place the point like actually like within the red points, like so you couldn't actually draw a clear parabola to separate them all.
So then it would depend on how big C was, whether the decision boundary would try and go into that area and get it.
So if C was huge,
If C was huge, it would probably go there. If C was like not that big, it probably wouldn't bother, because that's the trade-off.
if going there causes misclassification, how would the large C decide? Like, how to
So it would depend on, it's not that it would decide, it's that depending on how large your C is,
If you see
It de-
allows it to infinitely large. And
well, you can't,
if you try to reach the point, you have more number of misclassification.
right, if you, so in the, let's look at the objective again. So in the objective, this is trying to trade off here. This is trying to trade off between misclassifying points or sort of like maximizing your margin, right? So if C is like really, really large and you have a misclassified point over here, then the decision boundary might change to get it. But if it's not that large, then this will dominate. The first term will dominate, and then it'll just remain the same, or it'll stretch a little bit, but it won't get there.
So it's not completely clear like what it would do.
It would depend. You would actually have to set your C and then run it and see what it does.
But I assume the question is, I mean, what if you can't pick up the new green one without picking up some red ones? That one, are you just like looking and you're okay, one down for each, and whether if you make that decision based on the remaining ones?
So like, can you repeat the question?
Yeah, like you would have to pick up, if the decision boundary to get that one green point,
Mhm.
two red points, then it would be back to not doing it based on, then you're getting the red points. Think of it like that, like,
So like,
I mean,
So the
Even if
question
you
is,
had a high C,
mhm.
you would have to stretch all the way out to get the new green point, and in doing so, it would then misclassify some of the red points.
Mhm.
If your example is set up like that, then it would not stretch out to the new green point, right? Even if C is flat.
Oh, I understand. Okay. You're saying like so you're basically saying if I put a green point here and it's going to have to, in order to get that green point, it's going to have to misclassify like 3 in the middle. Yeah, obviously it won't do it.
Can you please define precisely the CIs? Is that sum over what exactly is that sum? What are we summing over? What are we summing over?
These, the CIs.
Yeah.
So you have to go back to your slides and look at the CIs. So the CIs are basically, I'm going to ask you to ask that after class. Because I would have to look at the slides. Yes. It can be different shapes, but we'll usually specify on the test. what shape it's supposed to be. So here they actually specified it's a quadratic kernel. So I honestly don't know. So I know you can have polynomial kernels, like kernels of degree 3, and then you're going to get a wiggly line. In terms of, I don't know. Sorry. Okay, let's do kernel regression. How much time do we have? Okay. Okay. Okay, so you guys, did you guys do this on the homework? No? I thought you had a kernel regression question. No? Okay. So, all right, so this is the question. It gives you the model. It writes in matrix form for the solution vector is the weighted least square. So this, I think I did last time I was up here. So what you want to take the derivative of this expression, okay? And on a test, you're not going to really have time to expand. Don't expand it. So this is from Matrix Cookbook. Because and then okay, so how you're going to get a minimizer is to then set the derivative equal to 0. W is a matrix. Yes. It's a symmetric matrix. What do you mean in your case?
In your problem.
No, W is a matrix. The weight of each training example on the diagonal. Partial derivative with respect to S. Oh, partial. Thanks, Sam. Salik. Okay, so just rearrange this. Equals Yep, it should be plus. And then your beta hat is equal to is that right? Let me check my solutions. Yes. Okay. Question asks you, when is above solution unique? And the answer is that happens when A transpose WA is invertible. Or so when the matrix is full rank. So good, this is straightforward. So the next question is a little bit harder, I think, just because you have to remember what gradient descent is. Okay. So how many people did this question? Awesome. Did you remember what gradient descent was off the top of your head? It's pretty good. Okay, so gradient descent is written like the following. So we have some x, and we want to go with a step size in the direction of its gradient. Okay. So this is one of those questions where if you run out of time, just write down that you know you don't have time to do the derivation. Okay, so 1 is equal to beta t minus, I'm just going to use alpha for the step size. The derivative of our objective okay, this is beta t minus alpha, and then here we're just going to plug in our derivative from above. Yep. Okay. So number 4 is, can you identify the signal plus noise model under which maximizing the MLE corresponds to the weighted least squares formulation? So it's basically just asking you to copy sort of. So you would write y equals beta 1 plus beta 2x plus noise. Yes, sorry. Can't see that very well either. Okay. Where epsilon is normal noise. And 1 over Wix. Okay, so the last question. like the question, and it was confusing to me. But you can mention one advantage and one disadvantage of non-parametric techniques. So one advantage, what? No, if the TA does not understand the question, it will not appear on the exam. Okay, so one advantage is there are no strict assumptions. On the form of the underlying distribution. Or regression function. And one disadvantage you can see it as long as I will write quickly. It's computationally expensive. And there's a large number of training examples required. Now you can copy.
So is this general for non-parametric techniques, like this disadvantage, or is it just this setting?
It's in general for non-parametric techniques. Okay. So there's a naive Bayes question, perception. Do you guys have requests? If I am to, I'll pick the. Yes. Yeah, we're not going to test you on bias variance. I mostly put that in so that you guys would get a question about k nearest neighbors. So what I would do is skip one and then do the k nearest neighbors. So let me just say bias variance is very easy. Let me do this really quickly. If you where's my figure? Okay, here we go. So what I would do for this question is I would go through it for your own understanding. So there's this figure, and if you guys have taken stats, you'll know this. Okay, so what I would do is copy this figure and do the problem with that figure in mind, and it's going to be actually pretty easy to do this question. And if you somehow look up the solutions to this problem, the solutions are wrong online. So I will put correct solutions up. Okay, so unless anyone objects, I'm going to go over the logistic regression question, because I think that's the hardest one. So we're not going to be testing you on, we didn't cover logistic regression, so we're not going to be testing you on anything that requires you to know a lot about logistic regression. But I like this question because it's very conceptual, and you actually don't need to know that much about the actual model in order to answer the questions. And that's totally something that we would give you. We could give you something where you don't need to know a lot about the model, but that you can answer questions about, given that you know concepts about machine learning. Okay. So consider this binary classification task. So we have the sigmoid function, and then we have something that kind of looks like a weird version of SVMs, only with a logistic sort of loss. And it's asking you, sorry, this is the wrong copy. First question it asks you is, what happens when you regularize the So what can you see? Okay, I want you to see this. Okay, so the first question is, what happens if you regularize W2? Okay, so first of all, where would the decision boundary go? So the points are linearly separable. W1
I mean that expression actually 0. Because I said y equal to half and t square will be normal. And you get that expression.
does W, no. So what are you trying to answer?
Huh?
Are you trying to answer my question?
Yeah.
Okay, so I asked where would the decision boundary go, given that we have this linearly separable. Okay. It's almost home time. All right, so it's going to do that. Okay, now the question is, what is going to happen to the decision boundary if you're going to regularize W2? So if you're going to regularize W2, the boundary is going to rely less and less on X2. And so it's going to go this way, vertical. Okay? No, vertical. Because X1 matters. So you can actually use X1 to move the decision boundary back and forth like this. So if X2 is gone, it's going to be vertical. So, and the question says, does the training error change? So yes, the training error is going to change, because if you have a vertical decision boundary, it's hard to separate the data with just a vertical decision boundary. Get an increase in training error. So for A, you're going to get an increase in training error. Okay, so now B, what's going to happen if you regularize W1? So the opposite is going to happen. It's going to be a horizontal one. But here, if you do a horizontal boundary right here, you can actually separate the data. So the training error is going to stay the same. Yes.
Like in this case, the training error won't increase a lot, but isn't the original one a better separator still?
Yes.
So it would increase, but by not so much.
For A or B?
For B,
No, for B, it's the training error is going to stay the same. Because,
is the first separator a better separator like the original one?
yeah, but I'm not asking you what's the best separator. I'm asking you what happens if you tweak the model this way. Because I'm trying to figure out whether you understand what stuff means, right?
We're just defining error as miscalculation or misclassification, so it's the same.
Yeah. No, his question was, why are we doing this? Because the first separator was the best. Okay. Now what we're going to do is we're going to regularize W0. So if you regularize W0, what's going to happen? So if we're not allowed to have an intercept, then what's going to happen is your decision boundary has to go through the origin. So you can think about twisting the decision boundary like this. And there's no way you can twist the decision boundary such that it goes to the origin, such that you get 0 misclassification. Error is going to increase. Because you're not allowed to use, so any information in the x2 direction, you can't use that, right? So you're only going to use the information that you get in x1.
Yes.
So
I'm trying to figure it out from mathematical formula here. Regularizing means so.
Regularizing means you're going to push that w to 0.
Okay.
There's going to be a penalty there. Yeah.
So then you let c equals 0, and then this goes away. So you have a sum of log probability.
Yeah. So if you have a high c on that particular w0 or w2, then that weight is going to be pushed to 0.
Okay.
Okay.
Wait, so it should be CJ, CI.
No, because it's saying you can only regularize one weight at a time.
Oh, okay. So just C is going to.
Yeah. Okay, so the next question says, if we change the form of the regularization to an L1 norm, and we're regularizing W1 and W2, as we increase the regularization parameter C, what is going to happen? So given what you learned from the first part, we gather that basically W2 is a really important direction, right? Because if you regularize W2, then the training error is going to increase. So what's going to happen first, I said that backwards. Okay. Okay, let me think this over. I said it backwards.
Regularize W2, you're going to have a straight line. I mean, the vertical line, so the error is going to increase.
Yeah, okay, right. Okay, the error is going to increase. But if you are going to regularize W1, so if you get rid of W1 and then we have just W2, we can still get the right, we can still get 0 training error. So if we're putting a penalty on both of them, which one do you think is going to go to 0 first? W2, right? So W2, this is 2A. Goes to, 1 second, 0 first, and then W1. Okay, question. Yeah. So what we learned from the first part was we can classify with 0 error on W1 alone. Right? W2 alone. Okay, yeah. Yeah, so we can, sorry, I have it backwards. W1 goes to 0 first, then W2, yeah. Okay, so we can classify based on W2 alone. So when you put a penalty on W1 and W2, the first one that's going to go to 0 is W1. And the second one that's going to go to 0 is W2. So none of the weights will be exactly 0, only smaller. So it's a L1 norm. So that means that it's going to be exactly 0. And I think that you just have to kind of memorize that for L1 regularization, it imposes sparsity. So that means that you're going to get exact zeros on the ones that it sets to 0. Yeah, yeah.
That's true of an L2 norm as well, right?
No, so L2 norm, if you keep regularizing it, you might actually get small values. They don't go to 0. So the intuition, it's hard. So this is actually covered in optimization class. So the picture you should be thinking about when you think about L1. So for L1, the actual objective sort of looks like that, and usually and this is a really bad drawing, I just realized. You're trying to minimize squared error. Looks like great. So that's why it sets it exactly. I'm not sure what the picture you should have in mind for ridge is. That you have another circle. What? Okay, yeah. Oh, okay. Right, so L2, it's going to look like this. Yeah, that makes sense. So then it can possibly get really, really small without going to 0. Thank you, by the way. Okay. And the next two questions, I would skip them both because Carlton and I spent an hour trying to figure out B, and we decided it was not a very good question. I took these from old exams. So, and the other reason is because B and C require you to know about logistic regression, and we haven't covered it. So I'm not going to make you do it. No, but so we're not gonna put something on there that's directly asking you about. But we can give you like a model that you've never seen, and ask you concepts about it, like we did here, right? You didn't have to know what like logistic regression was to be able to answer those questions, right? Yes.